Can you hear me?
Yes, perfectly. Please go
Okay,
ahead.
thank you. Yeah, thank you. I'm Hongying from the Department of Mechanical Engineering, National University of Singapore, and today is my great honor to share our recent work on standardizing the structure design of soft robots through origami. I mean, you may wonder why. I think maybe the first question come to your mind is may become like, why do we need to standardizing the structure design? Actually, the soft robots, I mean, after decades of development, they have verified their ability in the different scenarios. And also because of their inherent compliance, I mean, they are believed to be like the ideal embodiment for the AI in the next generation for the robots. And also because most of the design, they are biomimic, so they have verified their versatility in the different environments. But still, we are facing some challenges. As the rigid robots, I mean, after years of development, and the researchers and engineers bring the rigid robot to the real industry, and right now, I think maybe we are also at the cutting edge. Like, is it possible for us to bring the software robots also to the industrial applications? I mean, the Festo is a pioneer that working on this commercialization process. They have developed many of the software robots, like these two, this robotic arm and this robotic hand as example. But it seems their commercialization is not as smooth as expected. So right now they have released this Festo Bionic for Education toolkit with the aim to just educate the next generation of the software robotic engineers. And for us, we think that maybe the limitations that blocked the software robots from using in the real industrial scenarios may come from like the high hysteresis and the low motion accuracy that due to like the deformation of the body, especially if the deformation comes from the stretch domain deformation. And also a second reason may come from like the low payload capability. And the third reason may come from the low level of standardization. For this one, we mean like that, like the radio robots, we can buy the modules from the market, like the motors, the sensors, and they quickly assemble them together, and then we can get robot that can work. But for the soft robots, for the beginners, they need to learn everything about like how to design, how to prototype. Even for a mature researcher, if we want to design a new robot, still we need to build everything from the scratch. So right now we are thinking of, is there a way that we can standardize some design of the robot hardware to accelerate the development process of software robots? So with this aim in mind, and then we also motivated by the Lego toys, which we play during our childhood. When we play the Lego toys, we notice that we have many standardized modules, and then we just follow a map to assemble these standardized modules and integrate some actuation. We can get a toy or a robot that can move. So right now we are also thinking of like, is it possible for us to bring this kind of standardization and assembly concept to the design of soft robots? The answer may be possible. And if we follow this design design methodology, we will have two questions to solve. The first question comes from like, how can we design this kind of standardized modules? And the second question is, how can we assemble them together? So right now I will just like follow our first question. I mean, because we want these modules to be standardized, and actually the origami is like an ideal way because we can have many standard units to be used to develop such a kind of actuators. For this actuator, we call them Lego origami actuators. This is mainly because their structures are designed with the inspiration of some basic origami pattern. So for this one, we list the three. These three, as you can see, this one, the first one can generate a contraction, second one generates a bending, and third one generates some twisting motion. So by this way, we can decompose the continuum deformation into some fundamental kinematic movements. And the good way is like for all these modules that we listed here, they only have a single degree of freedom. So it means that for the actuation, it can also be very simple. For this one, we just use the pneumatic power to actuate all of them. And regarding the modeling of all these modules is also straightforward. Because they only have a single degree of freedom, we can actually use the radial robot kinematics to model these like a soft modules. So we can use this kind of very simple homogeneous transformation matrix to model the kinematics for all the modules. For example, here, if we look at this translational module listed here, it only have one output, which is the DC here. It can denote the translation motion. And also another thing is like by changing about the geometry, like this H and L here, we can also change this DC. And now let's look at a quick characterization about all these actuators. For all these actuators, we have tested one bending and one contraction. For both of them, they can sustain more than 10,000 repeatable tests, which make it like a little bit amazing among the soft actuators. And also their hysteresis is very small, and it can also sustain large payload, like it's more than 70 Newton force. And so that's why we believe that these kind of Lego-like origami actuators can really be used to build a soft robotic system. Now we have the second question. It's like, suppose we have all these kind of soft actuators, how can we assemble them together? So we propose an optimization-based assembly algorithm. For this algorithm, suppose we know the starting point and the ending point. So our objective is like to determine how many modules to be used and what type of the modules, and also the specific pattern of these modules. So these are the questions we need to answer. So for this optimization-based assembly, actually we divided this question into two steps. So first step is from the starting point to the end point. We try to build like a several reference points. This reference points, each of them will determine one pattern of the origami actuators. So for this one, this optimization problem, we try to minimize the length between the starting point and the end point. Suppose if there is some obstacles listed somewhere inside this configuration, we can just simply add another parameter into the optimization goal. And after we solve the first step optimization, we determine all the reference points. Then we also know the pattern of each of the modules and also their range of motion. And based on the range of motion and the pattern, we can refer to the kinematics model again to determine the crease pattern. After we have this crease pattern, we can simply fabricate them using the lamination method. So now let's look at their performance as a system. So firstly, we want to characterize the position accuracy for this system. We just built three actuator models manipulator, and inside this one, we decide the starting point as 0, and the one passing point somewhere here, and the one end point. So based on our two-step optimization method, we can determine the geometry for all these three actuators. And after we prototyping them, we have just test 10 times of the this manipulator, and we record their position error. And we can see that the position error is less than 3%, which indicate that this Lego-like soft robotic system, they can be very accurate. And then now we are wondering, how can their application scenario? So for the first application, we also use this one as a robotic arm, but for this one, we have an obstacle. And then we use our optimization to decide about their configuration. And after we assemble them, and then as you can see that it can avoid the obstacle and also place the object in the desired position. And later, a second application, it will be manipulator for the test-based inspection. For this one, we assemble the bending module and the contraction module all together, and also actuate them in a sequential way so that we can inspect the objects that is blocked inside this room. And finally, another case is like for the walking robot. We all know that the walking robot is a very complex system. But if we can use this Lego build modules, and then we only require to use 4 modules to build the joint, and then actuate them sequentially, just using these solenoid valves, and we can generate a walking. So to summarize about our work here is like we propose a standardized way to design the soft robotic systems. For this one, we can accelerate the design, modeling, and the fabrication process. And also we propose a way to assemble all these lab modules together to make them into the functional robotic systems. And also we tested their position accuracy and also their application in the laboratory scenarios. And if you want more information, you may check our published papers here. And thank you for your attention. It's the end.
Yes, thanks so much.